So here's what we're going to talk about today. We're going to kind of talk about our lessons that Pete and I have seen that we didn't think necessarily are taught in an OR program. And so, our idea here is that OR programs teach you OR, and we're going to kind of go outside of that and think, what are the computer science things and business elements that you need to get your code used in practice. And Pete and I have been working together probably 20 plus years, and we built optimization applications that were used by hundreds of different people across lots of different companies. And we've also built optimization tools that were used by just a handful of people. So we're going to share kind of our experience, what we've seen, and hopefully there'll be some lessons that will resonate with you guys and you can take back to your practices. So this is not our first lesson, so we kind of put a hard constraint on ourselves of 6, and we didn't want to use one of these, but we thought it was worth mentioning the fact right from the beginning that users like nice interfaces. So I think it's almost self-evident, but it's not always so easy to deliver that. And we found a quote like from this guy to be very helpful as we think about the interface. And his basic idea is that a good interface should be like a person that you like. They should be respectful, generous, and helpful. And we've kind of tried to use these principles as we've built interfaces over the years. And so what does that mean? So from a business user point of view, so someone who needs to interact with an optimization engine, the business user would like a way to input data. And the input data you have to design carefully because it can be both manual and automatic, or some combination thereof. And so you want to give the user the ability to input their data. You also want to give the user some kind of ability to control the optimization parameters, like sort of get in and sort of feel like they have control and actually give them control over the optimization parameters so they can guide it in the direction that they want and get kind of the answers that they need. And then finally, which sometimes it seems trivial, but other times we've seen OR professionals miss this point, is that users like to see what happened once you hit the run button and comes up with a solution. And what happened is not just a dump of the raw output files from a solver, but actually a lot of post-processing to put the data into terms that make sense to the user, or maybe even compare it to other scenarios and things like that. So there can be a lot of work in figuring out what goes into these, and you want to be able to present the output to the user in a way that helps them clearly understand what happened with the particular optimization run. Now, that was kind of for the business user who interacts directly with it. The other place that we've seen our optimization engines placed is sort of embedded in some other system or some type of consumer product, where in that case, the interface might not be your problem. So from an engineering point of view, as the optimization specialist, the interface is sort of out of your control, but you still want to maintain those same principles of, do your work well, and it'll be respectful, generous, and helpful to all the other engineers who are working around you to complete the entire project. The other thing that we like to stress and think about too is that sometimes when doing interface design, keep in mind that less can be more. So we've seen this, the classic one is Yahoo versus Google. When Google came out, had this nice, simple, clean screen that a lot of people credit it with, part of their appeal in the market. And we've seen this with optimization type tools as well, where there's some temptation on the left. And I have to admit, I completely fall into this temptation where you want to provide the user with lots of different fields and lots of different inputs and lots of different control. And if you can get away with it and still have a tool that solves the problem, if you can see something like on the right and have much fewer parameters to play with, you might get a better user experience. Now, we completely understand there's a trade-off here between the simplicity and user experience and being able to do what you need to do. But I think it's a lesson worth thinking about is, can you get away and design the tool so that you can have less and a more appealing interface so that the users enjoy working with your particular tool. The other thing we caution is, don't be too hard on yourself. Design is actually very hard, and it's one of the things that is hard about it is that with these kind of optimization problems that we tend to solve is that it's not clear what the user wants. It's not clear how to present the results. And so what you want to think about is if you can take an iterative approach to designing an interface. So here's the results of a particular output that we put together. This was an early version, and what it evolved to was the one on the right. And so the idea here is that if you can think about an agile type development process, so it doesn't have to follow all the tenets of agile development, but release something early and get feedback. And Pete and I have had good luck over the years. So we've released a lot of tools with an interface that was good enough, and then we let the users actually guide the interface. What things did they like? What did they not like? What would be better? What could be enhanced? And we found that getting user feedback was 10 times better than us sitting in a room trying to figure out anticipate what the user might like. And so this was our suggestion on this one, is just get the interface out in front of the customer, let them make suggestions, and then iterate. And when we talk about interface, we kind of mean all the elements. So we mean the overall GUI, the overall look and feel, but also how you interact with the inputs, like how you pull in data. Is it automatic? Is it connected? Is it a manual? Can you edit it really well? How much control do you have over the optimization engine? And then again, we talked about the outputs. We kind of mean all those elements. All right, so let's dive into lesson number 1. So our first lesson that we've learned over the years is, don't let users get themselves in trouble. And if you let the users get themselves in trouble, that trouble becomes your trouble. And I have a favorite story of this, and this was a long time ago when I was in grad school in the mid-90s. Dr. Jeffrey Kirenbauer came to talk to us at Northwestern. He's the president of Insight, the company that produces the sales network modeling tool. So he's been in the industry a long time, expert at this kind of stuff. He's built lots of applications over the years. And he told this great story that just has stuck with me over the years, and I think it just sounds so true. So this is, remember, mid-90s, and computer speeds were a lot slower and solvers were a lot slower at that point. And he was telling the story that he designed a system for a client that had some parameter, and this parameter, I can't remember what it did, but it controlled something that was important for the runtime. So maybe it controlled some group of integer type variables. And if you set the parameter to 9, you had 9 groups of these integer variables. If you set it to 8, you had 8 groups of these integer variables. It was a really tough integer variable for the solver to handle, which is why they limit it to a single digit. So the user could put in some number between 1 and 9. And then, so the client put in 9 and was playing with the tool. And the model, he said, I remember the model runtime was, in the 2-hour range or something. It was long, but not terrible. But the client just really needed to increase that value. So the client came back and begged them and said, look, we have this limit of 9. We just want to put in a 10 there, or an 11, or maybe a 12. We just need a couple more of these groups of tough constraints or tough integer variables that we can then do some more great modeling with. And they resisted for a long time because there was a reason he put it at 9. But eventually they relented. It's tough to resist customer pressure. So they finally gave them this 2-digit entry here, and so the customer could put in an 11 or 12 and so on. And then, time goes by, and pretty soon the client was calling because the model had failed. And, this parameter was one of many, but they spent a lot of time trying to figure out, why did the model fail? It was running before, it's not running. The client said, well, I didn't really change much of anything, and all of a sudden it stopped running. And so they were, trying to diagnose it, and finally they had to take a look at the model, and when the client said they didn't change much of anything, that parameter went from 9 to 99. So basically they did this, a 10x increase in the number of variables here. And the limit was set for a reason. And once you put it up to 99, it had 99 groups of these these tough integer variables, for example. The model just completely crashed and was never going to run. So this is an example of they tried hard to resist letting the users get themselves in trouble. Then they relaxed something, and the users immediately got themselves in trouble, and that trouble became his problem to try to figure out what was wrong. Now that was an old story. So if you come back to today, we still see this, and we've seen it a couple times recently when we're thinking of using a set covering approach for a model. This is like vehicle routing or constock, where in the pre-processing we generate like all the possible feasible routes, or cutting stock maybe generate all the possible cuts given some sort of constraint. So it's easy to imagine in both of these cases that you can have, in the average case, a very tractable number of feasible inputs. Say if you're doing a vehicle route and you limit yourself to 4 or 5 stops, then it could be a very tractable problem where you have 200,000, let's say, possible routes that you generate. But it's also easy to imagine if you're not careful and you give your users control, instead of putting in 4 or 5 stops as the maximum, for example, they may put in 10 or 12 stops, and all of a sudden the 200,000 feasible routes become 200 million feasible routes, and you now have a problem that's almost nearly infinite in its time it takes, from a practical point of view. So it's running for hours and hours and hours and days and days and days. So it's easy to let the users get themselves in trouble if you're not careful there. And sort of the other problem, to be quite frank, is just the fact that Gurobi's MIP solver is awesome. Like, it does great things. It can solve huge problems, and the benefit of mixed integer program is you can model almost anything. So it has this incredible amount of flexibility. And sort of where this gets us in trouble is, the fact that P still does not equal NP, and so we're still kind of bumping up against some of those limitations, and it gets us in trouble in design. And the way I've seen it show up to me is when I'm talking to someone who wants to build a model, and they're thinking about, what should be in that model, and we're kind of going through that design stage, and the questions come up, natural questions like, can I model all my products? So think about a retailer thinking about all 10,000 of their SKUs. And the answer is yes. I've seen Gurobi handle such large models. Like, for sure, we've had models that have handled that many SKUs. Then someone else asked, can I model 52 time periods? Like, yeah, time periods are very common. We've seen people model 52 time periods or 104 time periods where you're looking out 2 years in weekly buckets and so on. So we've seen lots of models like that, and it's pretty common. Can I do open, close, or use, not use decisions at lots of locations? So I have lots of these decisions I want to activate or not activate. So these binary variables everywhere. And the answer is like, yep, we've seen MIPS that it can handle, very large scale problems here with lots of different binary variables. Can I model fixed setup and switching costs? So I want to model some kind of switching cost. So if I go from A to B, that incurs some cost. It may be different from then going from C to A. And so, yeah, we've definitely seen that. There's ways to do that. It's a little complicated, but there's definitely ways, and there's definitely models that do that. And so it keeps on going, and can I ... like the questions keep coming along that flavor. And so you get this list of questions, and as optimization professionals, we know that each one of these questions by themselves is perfectly reasonable, and we've seen models do all of them. But what we also know deep down is that when I put them all together, I'm going to have problems. It's just not going to work. And so it's trying to figure out how do you get past this particular problem? Like, how do you think about, what do I do with all these different questions that I know together won't work? And it's not clear. I can't say, well, take all of them together, but instead of 52 time periods, have 26 and everything will be good. As you know, it doesn't always work like that. So what do we do about all this? So I think there's 4 different strategies to think about. So the first one is set up some guardrails. So this is like our first one. Just let the user, like in the first example, let the user only enter up to 1 digit. So only enter up to 9. Don't let, in the set covering, don't let the users kick off these near infinite loops of input. So set up these guardrails. That's one approach. Users tend to hate guardrails or can hate them, like we saw in the first example. So the other is think about building heuristics. So when you're solving large scale models, you can't, as professionals, we can't shy away from this part of the problem. We need to tackle it head on. If a problem is going to be too large, either in creating the input or maybe creating the output or solving the MIP, we need to start thinking about, how do we split up the model? How do we prevent us from generating all the possible solutions? So building in some heuristics into your model so to prevent the users from getting into trouble right from the start. The third approach that we've had a lot of success with over the years is also educate the users and say, yep, all those different possibilities are true, but if you could aggregate your products, that will help in some kind of significant way to reduce the size of the model. Or if you can get away with fewer time periods, that's going to be better. So let the users, educate the users on where the boundaries are, and then oftentimes your users will pleasantly surprise you and come up with models that are solvable, that solve their particular problem, and they made the tough trade-offs for you in terms of what can actually go in the model. And then the fourth approach is probably my least favorite one, just because I was on the losing end of it always. This was an ongoing battle that Pete and I had over the years with a particular feature. And the particular feature, so Pete and I spent a lot of time developing basically a strategic facility location tool. So a tool that let companies decide, where should they open up their warehouses and where should they open up their plants. And these models got pretty complicated. So there was, lots of decisions on lots of different potential locations, maybe decisions on plants and lines and lots of different products and lots of different customers. So large models. And one feature that always came up was better modeling of transportation. And specifically what that means is that users would love to put step sizes on each of the lanes in the model. So a lane is a shipment from like a warehouse to a customer, from a plant to a warehouse. And so this would be basically an integer variables that would model these step sizes. And the step sizes could even represent individual trucks. And so users really wanted this. I always push Pete to do it. Like, we can put this in. It's very easy to think about how you design this feature. It's not hard. But Pete pushed back. And so his pushback was, and I think rightly so, that if you put this feature in, the models just won't run. So you put all these other features and add this one in, the model will never run. He goes, what's the point of putting in a feature that will never actually run for the user? So even though the user thinks they want it, if they have it, they won't be able to get any results. And so this approach is just don't add that particular feature to the model. So it's definitely a tool that you should think about using as you design these. Are there features in the model that you should just leave out, because if they put them in, it won't work. All right, I'm going to turn it over to Pete now to talk about lessons 2, 3, and 4, the 3 Ps.
Okay, thanks, Mike. So this language here, be prepared, be proactive, and be paranoid. This is my language, but the lessons learned here, I think, are consistent with what people learn in computer science programs, and they're also consistent with the philosophy of agile development. So it shouldn't be too shocking to anyone that's coming from those two backgrounds, but these are the sorts of, some of these ideas I think can be fairly new to OR people. So for runtime, this is where, so I'm kind of starting off with the most heretical statement, I think. For runtime, people from OR backgrounds tend to be just obsessed with the code being as fast as possible, right? That's what kind of Gurobi's top line brag is, the fastest solver. When you're doing your job and building the model, you're engaging in a software engineering task, and it's a common truism of software that you don't prioritize runtime over all else, right? And so, because getting the code to be correct is also very important. And to some extent, there's only so much you can do with runtime, and you don't want to get stuck in sort of a wheel of diminishing returns where you're working harder and harder to make very tiny improvements to performance. So the lesson of software engineering is that the most efficient way to deal with runtime issues is to write a correct program that get your program well tested with good regression tests backing it up, so that in the future, if you need to reorganize your code, you'll be able to reorganize your code efficiently while testing it efficiently. And then look to see what the real world runtimes are. And in particular, what often happens is that there's a performance bottleneck where 10% of your code accounts for 90% of your runtime, or maybe the bottleneck's not quite that tight and it's 20% of your code accounting for 80% of your runtime. But regardless of what the actual number is, the idea is the most important thing you can do is to find that performance, is to do the due diligence step of looking for that performance bottleneck. And then if you have one, your life is much simpler, because there's no real point in trying to speed up the 20% of the runtime when you're still stuck with one small block of code accounting for 80% of your runtime. So this idea that you should get the code working correctly first, have the code be well organized, reasonably easy to understand, and then look for the runtime issues based on real world experience. This is embodied in the quote of Donald Knuth, premature optimization is the root of all evil. And in this case, he's not talking about optimization in the math sense, like in the Gurobi sense. He's talking about tuning your code for performance. And the idea is that you do that tuning with real world results once things are working. Now, note I'm saying with regards to runtime, you should be prepared. I'm not saying you should be reactive, right? So there's a reason why I'm not using the term reactive here, because that sort of has a negative connotation that, okay, all you're going to do with runtime is just kind of lay back in the high grass and wait around, and and then okay, I guess somebody's going to come down at some point and give me a problem, and then I'll pop up and address it, right? No, I'm saying, since you know that this strategy, this 90-10 address the bottleneck strategy, is what you're going to actually do with runtime, you should prepare yourself now with the tools and the idioms that you would use to go through that bottleneck assessment process, right? So the two halves of that are, first of all, how do you look for the bottleneck? How do you profile your code? And then what do you do once you've found the bottleneck, right? So how do you profile the code in Python is relatively easy. There's a great tool, cProfile, that I've used. In general, one of the reasons to use Python, beyond just in my opinion, the beauty of the language, one of the reasons to use Python is sort of the rich set of ecosystems. So I'm going to be referring to a few Python tools throughout this talk. And for assessing the bottlenecks, cProfile is quite good. That said, if you're using it the very first time when you're under the gun with the client, that's not going to be a happy experience, right? It's like most tools, it behooves you to play around with it, get a feel for what the output's like, get a feel for what the different parameters are like that you can use to run the tool. Now, with respect to what do I do with my code after I found my bottleneck, there's no one simple answer there, right? There's actually, so this the second bullet point here could be its own talk of, here are a bunch of coding strategies to speed up code, right? But I'm only mentioning here probably the one that's most specific to building mixed integer programming models, which is where you need to slice over sets of indices. And I can describe that. If people are not familiar with that terminology, what does it mean to slice over indices? You're probably familiar with it if you've looked at the netflow.py example with Gurobi, because that's the multi-commodity network flow is always the simplest example that requires slicing. And at any rate, this is the how to slice in Python. It's a nice thing that Gurobi kind of paved the way for us and invented a few good strategies for slicing with the Gurobi API. So the one that I use is kind of the original Gurobi invention for how do you deal with slicing, which is the tuple list. If you look at the netflow.py example on Gurobi's page right now, they're not using tuple list anymore because they have some more idiosyncratic, some more kind of Gurobi specific ways to grab a subset of indices based on a single index, right? But at any rate, when you're looking at that example and you see the little star there, that's a sign that they're using the slicing functionality. So This is where the conversations can become difficult with regards to runtime, right? Because you're only going to do so much with runtime. So absolutely, if you should always be doing this due diligence step every time there's a slow model, but that doesn't necessarily mean that you're going to always achieve the performance that'll make everyone happy, right? So what does the world look like after you've done the due diligence step of looking for your bottlenecks and trying to do the clever things that make the bottleneck code run fast if there is a bottleneck, right? So you tend to fall into these two general categories. One is, hey, there is no real bottleneck to this code, right? There's a bunch of processing time over here, a bunch of processing time over here, and a bunch of processing time over here. The only way I could imagine making this thing faster is to rewrite the entire thing in some low-level language, and that's just not within the scope of this project. So that's a good case for you're finished working on runtime problems. The second category that can happen is, okay, there is a bottleneck, but this bottleneck is not going to get any faster, right? So how does that break out? If there is a bottleneck inside the mixed integer programming section, so there is a bottleneck inside of the Gurobi performance itself. That is usually a sign that you've done your work well, because Gurobi is a very fast solver, and for sure it's possible you've created a really bad formulation, but it's also relatively straightforward to get a few people to kibitz on your formulation. Once you have the best possible formulation and you're solving it with an industrial grade tool like Gurobi, you're just dealing with the reality of P is not NP, right? So there's going to be a performance bottleneck there, and that's the time that it's going to take. Now, it can also come up where the user wants to use an optimization model in a way where the underlying mathematical model that they're creating is relatively simple. And what ends up happening is the Gurobi simply solves the model in its pre-processing step. So in that situation, it's actually natural for there to be a performance bottleneck outside of Gurobi, right? The user could be presenting you with very large input tables, and these tables need to be boiled down into this core mathematical model. But once that boiling down process has occurred, Gurobi can then do its work very quickly. And just because Gurobi is able to do this kind of sexy math part super fast, that doesn't magically mean that other things that need to take time will no longer need to take lots of time, right? Boiling down a big input table is just something that's going to take time. So there are situations where you have a bottleneck outside of Gurobi and you've studied it, and this is, the pre-processing, the model building, for example, could be a reasonable bottleneck to have in your application. So this is the sort of situation where what you really need is, if the users are just not happy with the runtime, but you have good reason to believe that the runtime is just not going to get much faster, this is where you want to have a good salesman on your project, right? And that's true of a couple of these bullet points that I'm going through, is that it's important to have somebody to kind of sell the process to the client that understands the reality of the underlying engineering. And you can refocus on how optimization is a game changer for businesses in a lot of situations. And you can say, sure, I understand that you're used to, using your phone, and when you hit the button, everything happens immediately. This is not exactly like that. You'll hit launch and you watch progress go by, but the whole thing takes an hour and a half. But what are we getting done in that hour and a half? We're generating results that drastically improve your business. So this is an hour and a half of time well spent. Okay, so now with bugs, I'm changing direction. I'm kind of changing my orientation to be the exact opposite, right? So with runtime, I was saying, you know what, you should be ready to respond, right? With bugs, I'm saying you should be completely proactive in trying to test out your code so that the user experiences, from at least a mathematical sense, you're releasing to the user zero defect software. So why is catching bugs so important? It's generally true in software that this phrase, go slow to go fast, is not my invention, right? This is kind of, I think, one of the classic phrases of Agile. And the reason why they say you should go slow to go fast is because when bugs get released, they are time consumers for multiple peoples in the organization, right? And I think this is even more true of these math optimization bugs, where the bug gets released, client complains about it, a tech support person, discusses it with the client, then an email gets sent to a development engineer. Then there's a company meeting about, okay, how important is this bug? How many other people do we have to alert about it? Okay, now we have to write up, when does the bug occur? When does the bug not occur? And now this bug report, until it gets fixed, the existence of this bug remains kind of like a detritus in your organization, whereby other problems that come up, the investigatory process gets confused because it's like, okay, is this a new thing? Or is this that other bug re-manifesting itself, right? So released bugs just slow everything down. Now, in optimization, there's kind of a double whammy for releasing bugs, because not only will they slow down the development process, but they destroy your credibility with the client. Now, we have to bear in mind with optimization, we're selling a fairly expensive service, and we're sometimes colliding with resistance in an organization where optimization, where these artificial intelligence tools are seen as challenging to the business experts that are making these decisions right now. When you release bugs, you're damaging what could be a potentially fragile relationship from the very beginning. So to tie it back to Agile, my second bullet there, it kind of looks like I'm reducing all of the world of Agile development to just a single sentence. But if you'll bear with me, I think you'll agree that there's a lot of wisdom in simply paying attention to the simple fact that you should not release untested software. Now, I'm being a little bit extreme there, and I know people aren't actually going out there and releasing software that they don't test at all. But I do think there is a tendency to release under-tested software. And when I get to the next slide, I'll talk a little bit more about, like, okay, why is this software under-tested relative to what are really best practices? Now, my final point here on this slide is that we've got a little cute rhinoceros there, and I've kind of invented the phrase, rhinoceroses become Jedis, right? So this is in reference to rhinoceroses are famously thick-skinned, right? So what am I getting at with that? This is an area, dealing with the repercussions of released bugs is an area where kind of emotional health and professional development diverge, right? So I think the world of psychiatry would agree that it's not emotionally healthy to dwell on your past mistakes, and at some point you kind of relatively quickly achieve your lesson learned and try to refocus on the rest of your life. Whereas with software, with releasing these sorts of bugs, I think it really behooves you to study, okay, how exactly did this bug get released in spite of my best efforts? Because my experience, one of the things you really do get better at as you do this more and more, so this is an area where wisdom comes into play, you get better at designing your software so that it can be tested more effectively. So I know that's the sort of thing that could be its own talk, right? But some people, you might expect that as you write more software, you just simply get better at not writing bugs. But there's always, the writing of a bug it's just always there that you could sort of make a goof, right? But the thing that you can get better at is knowing how important bugs are and thinking about, okay, if my code is organized this way, then this testing strategy will be very efficient. So another area in which you can improve the quality of your software, and this seems like it should be obvious, but I think it's really easy for organizations to skimp on this, is to undervalue the utility of having somebody dedicated simply to testing, right? So the natural tendency is like, oh, this is a big project, we'll want to add manpower to it. Okay, let's have 4 developers on it. Okay, how many testers do you have? Oh, we didn't put any testers on it. We just have 4 developers. No. In fact, having 1 developer and 1 tester, even that high of a ratio, can be very valuable, I think, especially with optimization, where the models are very tricky and knowing what is and was not a bug is a fairly complicated process. So what is the value of having this outside tester? So having somebody that's not the developer testing the code. For the non-American audiences, this might not be quite as famous, but this is the space shuttle disaster in 1986. And in the follow-on, in the post-mortem, which went on for quite a while, the physicist Richard Feynman demonstrated how the O-rings failed in the cold by dropping the O-ring plastic into a pitcher of ice water, right? So this was something that wasn't properly anticipated by the space shuttle engineers, that even though they're flying in Florida, that sometimes you have cold days in Florida. So this is the sort of thing an outside tester will bang on your code in ways that you didn't anticipate and force you to add functionality of the flavor of, okay, I added this switch here that looks for the temperature and says it's too cold today, I'm not launching, right? So the analogy to that would be to add sort of very rigorous data integrity checks, which I'll talk about it in the section after this one. So this is a practice that does seem to be a bit underused in the OR world and has become very, very common in the world of computer science, which is you use code to test code, right? So particularly in Python, this is a deep cultural part of Python, is that Python does not have a compiler. So even the simplest sort of misspellings in your code will generate bugs, will not be caught until you actually exercise the code, right? So you really do have to exercise all the code before releasing it to the client. So the phrase "tears and rain," that's a quote from the movie Blade Runner. You know, the idea being that I agree that people will test, right? People building these math models will test, but oftentimes what they will do is they will have kind of a manual process of testing that they go through for their engine, right? They'll be following more or less the agile methodology. So they'll be adding a feature and then testing and adding a feature and then testing. But every time they go back to the testing step, it's kind of tedious and repetitious. And so as a result, the tendency is to keep that testing sequence that they have to manually go through relatively simple so that they can go through it quickly. But in fact, using good tools, which are readily available, especially with Python, the testing process should be, I hit a button and I looked and it said okay, or it didn't, right? So the regression testing process should be that simple. Now, in Python, this is relatively easy to do with the unit test package. It's all one word, lowercase unit test. So I use unit test as a way to automate the running of my regression test models. The other thing I do is that it's natural when you're using real world data as part of your regression tests, it's natural to have useful tests that take some time. So it's very easy to say, oh, this was a great model that got run here. It ran and it actually hit this very funny corner case bug. And so now I'm going to remember this bug fix forever by incorporating this testing model into my test suite. But hey, it takes 25 minutes to run. Okay, that would be a killer if you were doing it by hand. When you're automating it, okay, I'm adding a 25-minute model. Now I'm adding a 30-minute model. Okay, I have an automated process that I go through, but when I hit run, it takes now 3 hours for me to see whether I got a full clean result. So the way I handle that is I break my unit tests up into the fast section and the slow section, right? And the fast section gives me pretty good confidence that my code is correct. The slow section, I don't have to run on my computer. I can run that off in the cloud using the Jenkins server, right? So my sense is that Jenkins is something, I've used Jenkins with 2 different organizations now with building Python engines. My sense is it's not super common among the Gurobi community to connect unit tests to Jenkins, but I think it ought to be, right? Because we're building the types of engines where we don't expect them to run fast. So we are going to have the slowest regression tests of anybody, right? So Jenkins is particularly important, I think, for this community. Okay, so I've been going on and on about how, don't release bugs, they're bad, put extra effort into not releasing bugs, zero defect software development. It's important to point out that with optimization, the clients are particularly prone to not knowing what they want, right? So you could build the model mathematically correct, you made 0 mistakes, you did exactly what their phrasing implied in a mathematical sense, and it wasn't until they saw the rules that they described in action that they realized that they gave you an inaccurate description of how the objective function should work, or they gave you a crude description of how a constraint should work and they actually need something more refined, right? And then you have to go back, and even though you did it right the first time, you have to go back and change things and use some different equations. This is not a space shuttle exploding sort of example. This is more like the way the natural process is supposed to be. And so, one of the things when I'm with zero defect software, I said, yeah, you should go back and beat yourself up when you release a bug. This is not the sort of thing where you have to go back and beat yourself up, right? Instead, this is again where it's good to have somebody who is part of the engagement, who is a good salesman, who can then work with the client and say, look, we are doing zero defect software on our end. We're not sending you bugs. It's just a matter of we're discovering together how to write these fussy equations that will properly address your business problems. Okay, so up till now, I've talked about how runtimes, I think the best practice there is to be prepared to react. With true mathematical bugs, the best practice there is to be aggressively proactive in trying to suss out all the bugs, and you should have a kind of a cultural expectation that you're not going to be releasing bugs. With solver failures, it's kind of a blend of the two, right? So this is why I'm saying be paranoid. By paranoid, I'm saying you should be both proactive and be prepared, right? There are things you can do to try to prevent solve failures from happening, but you should also be prepared that solver failures are going to happen and that there are ways that you can react to that to improve your software incrementally over time with respect to solver failures. And the general rule of thumb to bear in mind is that users hate these null results, they hate infeasibilities, but they will appreciate insights, right? They will appreciate it if they hit solve, okay, they didn't get an actual action plan, they didn't get a true result, but they did get some useful information about their model that they didn't know before. So with that in mind, a characteristic of a good solver, and again, you're not going to necessarily get this right out of the box, but you can progress towards this goal over time, is that a good solve engine always has something helpful to say. So where do solve failures come from? I'm breaking this out into two general categories, dirty data and infeasible models, right? So let's talk about dirty data a little bit. Dirty data, a good example of dirty data is, for example, a column that shouldn't be zero. So you can imagine there's a products table that has a weight column, and the natural part of building the optimization model is to include sort of like the shipping cost per weight, right? That will be an input to the Gurobi math, is shipping cost per weight. So you'll be dividing by that weight column when you're setting up the math model. So of course, since you're dividing by weight, weight should never be zero, right? So what's the right way to handle that when you're setting up your model? There's when you're building your application, there's three general strategies, right? Well, really two strategies and a failure to strategize, right? So the two strategies that you can use are, one is you can lock the dirty data rules into the GUI itself. So you can design your GUI so that there's the cell that would accept the zero simply won't accept the zeros. So the user tries to enter it and it doesn't happen. Instead, an error message pops up right there that says you can't put a zero here because this is weight, right? That's totally valid and it will work. There's a little bit of a downside there in that you're not really helping the user clean the data per se, right? You're forcing the user to do all the data cleaning outside of your tool, and then the data can't be entered into your tool until it's clean. What's a better approach, I think the more modern way, and what we're striving for here with OpEx, is to allow the user to enter dirty data and then to help him clean the data on your app if that's what he wants to do. So with that approach, if a zero is entered in the weight column, instead of that zero being rejected by the GUI is smart enough to light up that data cell and say, yeah, here's a red cell right here, that's a zero, right? That's a zero when there isn't supposed to be a zero. And all of those different failures that can happen in aggregate can create a nice summary report for the user. They load up their data, and then they see these different types of red cells summarized. You know, they can say, okay, you had 52 examples of this types of problem, you had 12 examples of this types of problem, and then the user can clean the data right there on your app, and he can progress slowly. Your app can be used as a storing place for data that's partially cleaned. Now, of course, what could very easily end up happening is the bad choice, which is just assuming that a zero won't be entered there, okay? We have sophisticated users. They know that no product weighs zero, so they're never going to enter a zero. That's not a realistic assumption because dirty data is just a fundamental part of modeling. What happens is that the user is collecting data, possibly from disparate sources, and there might be a missing product weight for a given product, and the user just enters a zero there as a placeholder, right? So this is why I think you should treat dirty data, the checking of dirty data, in a completely proactive manner, in exactly the same way that you would treat writing mathematical bugs. You should rigorously assess all of these simple data integrity rules of your input data before launching your solve. So now talking about infeasible models, right? So with infeasible models, the strategy kind of breaks out in two ways. There's sort of the sexy way that is appealing from a mathematical perspective, and then there's sort of the reactive way. There's the sort of prepare to react way where you anticipate that there are things that are going to come up that you couldn't prepare yourself for, and that you had to add code as needed to address real world concerns. So what's the sexy way is adding slacks to the model, right? This is something everyone's taught when they're taught about optimization, is that, in fact, you can make all the models feasible by introducing variables that minimize infeasibility and then penalize those variables that control infeasibility. Now, this can work well, but it only works if the user actually understands what's going on. So bear in mind, your users don't necessarily come from an OR background or any kind of formal math background, and trying to explain to them that, okay, this is a variable over here that allows this equality to be an inequality, that might not really land in any meaningful sense with them. So use slacks only when they make good sense from the business user perspective. Don't introduce slacks just for the sake of saying, okay, look, we are always giving a solution. Because if the user doesn't understand what the slack variables mean and what that slack minimize infeasibility objective function really means, then they won't be able to get any value out of the solutions that you generate. That's sort of the be proactive approach, is that you can introduce slack code if it makes sense. The be prepared approach is that you should anticipate that users are going to show you over time what are the common sort of infeasibilities they generate, and what sort of reports will help them in diagnosing those infeasibilities completely outside of the Gurobi solve process, right? So this is what will happen is users give you infeasible models, and you will have a detective mission to discover where the infeasibility comes from, and you will respond to the user with, an email and usually a table that says, look, this subtotal didn't match up with this subtotal. These subtotals were out of whack for these 5 products, and so therefore these out of whack subtotals are a good summary of why your model isn't solving. So that detective mission itself can be turned into code where for every model, assuming, this could take a little bit of processing time, so you can control this behavior with a parameter, but assuming that they have the most aggressive parameter setting turned on, you could simply go out and walk through all of the different data checks that you built in response to users' complaints and give them suggestions of, okay, here's a table that's summarizing this sort of data condition. Here's a table that's summarizing that sort of data condition. And these are the various problems that might result in an infeasibility in the true optimization step. Now, bear in mind, this is not the same thing as the solutions, right? So you might end up with a situation where you have the solution is like as many as 6 tables get populated, and everybody understands these 6 tables, and there really doesn't need to be much explanation for them, and they're usually all filled. Whereas in support of the optimization, there are like 16 different checks that happen, and each one of those checks is kind of complicated and not easy to understand what's going on. And most of the time, all 16 of those checks are clean and don't result in any warning tables that are generated to the user. So it's important that you don't let the checking of these 16 things sort of drown out the reporting of these 6 real results in the design of your GUI, right? So that's sort of a design challenge that you should be prepared for.
So we got 2 more lessons here, so 2 more quick ones. So the first one is the fact that you'll be swimming in data. So this one comes from the fact that what we see oftentimes is that people think of the MIP engine as like some kind of math, and if I just somehow feed the data into the MIP engine and I'll solve all the different problems. But in reality, when you're working on these type of problems, you're going to be spending a lot of time working with data. And the MIP engine, I think Pete said this well, it's just one more tool that generates insights about data. And you want to think about what other tools do you need to generate insights. This could be in the pre-processing in the design phase, and it could also be as you deploy the tool that you might want to have other tools to sort of provide insight around what the MIP engine is providing. So Pete he's more new school. He likes, using raw Python. He understands and gets pandas and SQL. I like to always put the plug in for the old school stuff that, Excel can still be pretty good, or Ultra can be good for helping analyze the data. And the second thing about the data that you want to keep in mind is that you want to make sure that the data is easier to read, so that, when you're post-processing, trying to figure out what went wrong with the model or how to explain the model, that at least you can understand the files. And so Pete has a couple of quick examples here.
Yeah, so the 2 programming tricks that I've found have helped me a lot. One is, I call it ObFuSimplify, and this is simply the anonymizing and relabeling of the user's data. So the easiest way to think about this is, suppose the identifiers for every person was their social security number, so that's a 9 digits identifier that, first of all, you don't really want to archive that in your regression tests because that's sensitive information. And second of all, 9 digits is just hard to read, right? You might only have like 50 people in your data set, and it's much easier to read your LP file if all of those 50 people are identified as P1 through P50, right? So ObFuSimplify is a coding technique where you do cascading replacements throughout the code. So for example, if you think of the diet example, you're changing all the food names to be F1 through F50, but those changes also need to happen in the nutrition quantities subtable, right? Because if you change it in the food table, but not the nutrition quantities table, you've created a referential integrity failure. And again, now you've created, dirty data and the model won't work, right? So model shrinking is again, the same sort of thing. So it's a common trick that you have a difficult infeasible model. The best thing you can do is to try to make a smaller model that shows the same feasibility. But shrinking down a data set can be a little harder than you think, because again, go back to the diet example. Okay, suppose I have 50 products, 50 foods over here, and I want to shrink that down to having only 5 types of foods. But when I remove the 45 of those foods from the table over here, that should automatically remove all the appropriate entries in the nutrition quantities table over here. And you could have a great deal of tables with a lot of these referential integrities. And so that's why you want to have some sort of automated code for doing cascading deletes throughout your data set.
Yep, and then the last example is like making sure you remember the data and the design. So you don't want to think about, here's an example of what you don't want to do is you think you want to build a model with really detailed features. Like let's say you're modeling a production facility, you want to model right down to the machine level. And then you go out and you build such a model with all this detail in it. And then only at the end do you realize that you're just never going to be able to get the data at the machine level to feed the model. And so you spent all this time building wasted features. And so instead think about, what data do I actually have, build the model there, and then start to expand it with more details is a way that we've found helpful over time. Our last message is basically take advantage of modern tools. So switching technologies is painful. So Pete and I have done it many times over the years. So we've had map info interface at some point, a VB and access interface, a .NET, a cloud-based. We've kind of migrated from time to time, and it's a total pain. I can tell you there's lots of fights and arguments every time we did it, because when you're doing a new platform, you don't get new features, you don't get speed up, so the clients might not even see it. But in the end, it was almost always seemed to pay off to sort of stay on top of what the modern technology is. And if we look at, where we progressed with technology, back in, say, 2003, there was basically two camps. There was consultants who used Excel and did crazy things with pivot tables and queries, like really sophisticated analysis techniques, and then developers were doing more low-level coding, worrying about things like memory management. And what we've seen over time is that both have kind of converged into using Python, where there's now this more easily sharing of information, more do-it-yourself, where the consultants can actually get some of the math models built and turn those over to developers to finalize. But this doesn't mean we're done with platform changes. So even though Python has momentum, it's a big ecosystem, we still have to worry about, has one library made another one obsolete, and when do we switch over with that? And then I think, my experience has been that, as with all this technology, is that there's going to be something else that comes out there that we have to think about, and we have to make a tough decision at some point. Do we switch some kind of underlying technology over to this new thing so that we can stay on top of what's going on in the community?